Okay, since I messed up the proof during the class, let me do this again. What I want to prove here is the Fourier inversion, which is to say that if you have the Fourier transform of f of x, which is by definition, it's the integral from negative infinity to infinity of f of x integrated against e to the isx dx. So you end up with a function of s. But then there's the inversion, which is to integrate this again against e to the negative isx, and this time we integrate over s, and you divide by 1 over 2 pi. So this outside part is the Fourier inversion formula. And I want to prove that this is equal to f of x. Now, to do this, we'll have to assume some things. First of all, we proved that integral from negative infinity to infinity of sine x over x is equal to pi, and that was done by using the Laplace transform and confinement trick. We did it a couple of lectures ago. And we're going to assume that f is smooth, which means you can differentiate f. And what I really want to say is that f is a Schwarz class, which means that it decays to 0 faster than any exponential function. With those good conditions, we can show that this is true. Now, but before I prove this, I want to do some changes here. See, this x and this x, these two are different because here you've already integrated x away, so x doesn't exist anymore after this, and then it's a function of s, which you integrated against negative isx. So this becomes a point of confusion, so let's just replace this x by y to distinguish them. But if I prove that these two are equal, then it should show the original thing that I want to prove. Okay, so eventually I want to start from here and prove that this is equals to fy. And the proof is that. Okay, so how do I do this? Well, first of all, since I've made this as y, now I'm free to bring this into the integral because y is different from x, so the s and y are considered as constant in the view of dx, so you can just bring it inside, and that gives you 1 over 2 pi integral they have the same base e and they both have is, so if I factor the is out, I get x minus y dx ds. And let's do a change of variables where u is equal to x minus y, so that dx will be same as du. And then if I solve for x would be u plus y. I also have to change the endpoints because this is a definite integral. And when x is negative infinity, y is considered as a constant, right? So if you have negative infinity minus a constant, that's still negative infinity. If x is infinity, infinity minus a constant is still infinity. So the boundary, although I do have to change it, it turns out that it doesn't change at all. So under this change of variables, you have 1 over 2 pi integral from negative infinity to infinity of negative infinity to infinity of f of u plus y times e to the isu du ds. Okay, and then here I'm going to do something that may not be fully justifiable, but I'm going to change the order of du and ds. If you think of this as some finite integral, it's actually quite easy because the endpoints do not depend on u or s, so you can just switch the two integration without having to worry about the bounds. So we're just going to switch s and u. And once s is inside, then you can say that this has no s's in there, so you can just bring this outside. Okay. so we're going to do that while also changing this infinity and negative infinity as a limit n going to infinity of 1 over 2 pi, negative infinity to infinity, negative f of u plus y, negative n to positive n, and then e to the isu du. And this one, it's easy to integrate. So integral of e to the ax dx is 1 over a e to the ax. So using that, see, we're integrating with respect to s, sorry. We're integrating this with respect to s. So iu is like this a whose reciprocal should come out. So I have limit n going to infinity, 1 over 2 pi. Times 1 over iu e to the isu, and to this I'm plugging in the endpoints n and negative n, but see we're integrating by ds, so these are values for s. So s is n, s is negative n, and you still have to integrate by u afterwards. And now let's plug this n into s. So these iu's, they don't cancel, so I can bring out the iu outside because that's the same, that's like a constant here. So we limit n going to infinity, 1 over 2 pi, negative infinity to infinity, f of u plus y, 1 over iu, and then you plug in n, so e to the inu, iun, let's use inu, minus e to the negative inu. But then that looks familiar because if I bring this I back here and put a 2 here and put a 2 down there, this is exactly sine of x formula, right? From the Euler identity, I gave you 2 formulas before where e to the ix plus e to the ix over 2 is the cosine, and if you do e to the ix minus e to the negative ix over 2i, that gives you the sine. So this is really the sine. I can cancel the 2 here and there. And that brings us to the following integral. It's limit n going to infinity, 1 over pi, because this 2 canceled away, integral from negative infinity to infinity, f of u plus y, and this is sine, and it's over u, so we have sine of nu over u du. Okay, so we have to compute this one. And at this point, what I want to do is I want to do integration by parts. Remember, integration by parts says if you have 2 functions multiplied, you integrate only one of them, and you plug in the endpoints and minus. You differentiate the other one that you didn't integrate, and then you bring the same integrated one here. This is the usual integration by parts, which I'm trying to bring here. But what you see is that I don't know how to find the antiderivative of this. So unfortunately, we'll have to make one up. So for the time being, let's try to define g of u as this unknown antiderivative sine nu over u du. But it's really, it can be any integral, right? So instead of writing it this way, I want to write it as a definite interval. So let me replace u's by t's. And then we want to make the integral from negative infinity to positive u, so that it's a function of u at the end of the day, right? And you can check that the derivative of this right side function using the second fundamental theorem calculus, if you differentiate this, u just replaces t, and so you do get the derivative of g of u as sine mu over u. So that's fine. And another property that we should think about is you might be a little worried about this negative infinity. Well, see, because you have t in the denominator, as t goes to negative infinity, this overall becomes close to 0. So this integral actually does converge to negative infinity. Actually, it does converge even if you integrate from negative infinity to infinity. That's a result that we got before. So it's okay to integrate from negative infinity. Alright, so once we call that as g of u, and then we apply the integration by parts, here's what we get. We get 1 over pi. You have f of u plus y times g of u. It's just like a placeholder, which we don't know. We plug in infinity and negative infinity. And then minus integral, the one that you didn't integrate has to be differentiated. So f prime of u plus y, it's still g of u, du, integrated from negative infinity to infinity. So that's what we get if we use the integration by parts. Now here's where we use the property that the function f goes to 0 when u is set to infinity. So although it's multiplied by some function g of u, we're going to assume that f of u is something that decays like super exponentially, so even if you multiply by any exponential function, it goes to 0. So that if you plug in infinity, it goes to 0, and if you plug in negative infinity, it goes to 0 as well. So that means this will just go to 0. And then we just have limit n going to infinity of negative 1 over pi integral negative infinity to infinity of f prime u plus y of integral g of u, I wrote there, negative infinity to u of sine of nt over t dt. And then you integrate by du. Okay. Now we're going to do another change of variables. We're going to set, let's see, I'm running out of numbers. Let's say, not y, z. I'll just say z is equal to nt. Then n is a constant, so I have dz equals to n dt. And then so dt would be 1 over n dz. So what happens here is that if I multiply n here and multiply n here, this part will be dz, okay? And this is z, that's z. The only change is that because this is the value of t, if t is u, then z would be nu, right? So this integral here will become equals to limit n going to infinity of negative 1 over pi integral from negative infinity to infinity of f of u plus y times integral from negative infinity until nu sine z over z dz, and then du. Okay, now this looks a lot like the result that I'm trying to use, right? So let's think about what happens to this thing. This thing here would be think about what the case when u is less than 0. Oh, so what I want to do is I want to move this limit inside. That's another thing that's a bit dangerous, but let's say we can do that. Okay, so if we bring this inside, because this is the only part that depends on n, right? If u is negative, then n times u would be, if u is like -1, -1 times n would be negative n, and as n goes to infinity, it would be, this part would be negative infinity. So if you take the limit, you end up with negative infinity on the top and negative infinity on the bottom, but that integral will be 0 because the top and bottom are the same. On the other hand, so this would make the integral be 0. This integral will be 0. If u is positive, then when this is positive, say u is like 1 or 2 or some positive number, then n times that number, and as n goes to infinity, you end up with an integral from negative infinity to positive infinity, and then that's the integral that we have here, the integration from negative infinity to positive infinity of sine x over x dx. We prove that it's pi, so this integral will equal to pi. So what that means is that when the u value is negative, the integral doesn't exist at all. So we can ignore that half of it. I mean, you can split this integral as integral from negative infinity to 0 plus integral from 0 to infinity, right? But this integral is gone because at those points, for those values of u, this integral gives you 0. So that doesn't exist. And when u is positive from 0 to infinity for the value of u, the integral that we have, as n goes to infinity, it will converge to pi. So that's what we have, and 1 over pi cancels pi. Oh, sorry, there should be a prime there, I forgot. There was a prime here, right? So with this prime, if you take the derivative and integrate back again, you recover the original function f with a minus in front, and you plug in infinity and 0. And once again, our assumption is that f of infinity is 0, so that doesn't give you anything, but then, so it's 0 minus f, and then when you plug in 0 for u, it says y. But there's a minus there, so it would be minus of minus f of y. So finally, it will be f of y, that is the result. And that concludes the proof.